done a lot of solving of right triangles now. But what happens if the triangle we have is not a right triangle? That happens a lot because not every triangle we're going to run into is going to have that 90-degree angle. And because of that, it means we're not going to have a hypotenuse for every single triangle that we have. But we still have to have ways of solving those triangles as well. Those triangles are called oblique triangles. And an oblique triangle is just a triangle that doesn't have a right angle. It is not a right triangle. So here's an example of one of those types of triangles. And what I've done here is, it doesn't necessarily have to be drawn to scale, but I have, just like we've been doing, labeling each of the vertices A, B, and C. And then we're labeling the sides opposite as A, B, and C, the lowercase letters. So we have this oblique triangle. We have a problem with being able to name what we would have here as far as SOHCAHTOA because we don't have a hypotenuse. So what's an opposite side? What's an adjacent side? What's a hypotenuse when you don't have the hypotenuse to base that off of? So we need something else to use. Something else that we can utilize in order to be able to solve this triangle. And what we have is the law of sines. The law of sines states that the ratio of the sine of an angle compared to its opposite side is equal across everything in the triangle. So that means that the sine of angle A divided by A is equal to the sine of angle B divided by B is equal to the sine of angle C divided by C. That ratio each time of an angle and the side opposite. The angle, its side opposite. The angle, its side opposite. And using sine as part of that. And you can throw this into this formula in this way, or you can throw it in this way. It doesn't matter which way you use it. Whichever way is it's easier for us to be able to solve things is the one that we're going to want to use. Our goal here is to be able to use two of these as a proportion. And then we would have one unknown so we can solve for that missing value. So that what that would mean is if we have sine of A over A equals sine of B over B, and we need to solve that part of it, we would need 3 out of the 4 parts of that in order to have one unknown and be able to solve. So that's our goal in each one of these situations, no matter which iteration of the law of sines that we're going to use. Let's take a look at an example. The first example of the law of sines that we're going to use is when we are given two angles and the non-included side. Something that when you were doing things with proving triangles congruent to each other, angle side was how you would look at it. It's a similar sort of thing, but we're not proving triangles congruent. But we're given two angles and we're also given the non-included side. So here's an example of this. Angle A is given to us as 32 degrees. Angle B is given to us as 75 degrees. And then side A is going to be a value of 8. So the first thing I'm always going to want to do is I'm going to want to label what's going on. You'll notice that I've set this up already, just like we've set up a lot of our problems in the past, where we're setting up all 3 sides that we have to find and all 3 angles, and then we're going to fill in what we need. So I want to find the parts that are easiest to find first. So I could use the law of sines right off the bat, but I'm not going to, because right now what I notice is I have angle, angle, I have another angle. So I can use the triangle angle sum theorem to figure out what that missing angle is. And when I put that together, I get 180 minus 75 minus 32, and that gives me 73 degrees. Very clearly, this is not a right triangle. Notice that 73 degrees is an exact value. So if we want to use 73 degrees as an exact measurement, we can do that later on. So we don't have any problem in not using any estimated values. Again, we want to try to use as many exact values as possible. 73 is one of those values. So at this point, now we want to use the correct law of sines to find the missing sides. I have side B that I need. I also have side C. I can find either one. I'm just going to use the given values that I have. And I'm going to use A, angle A. That is going to be my key value for my law of sines. Because I know that the sine of angle A over A I have that entire value right now. I can fill out that entire fraction. And that's going to be equal to the sine of angle B over B. That's the first one I'm going to start with. And then I also know later on I'm going to be able to find side C in exactly the same way. So I can also set that one up. Sine of angle A over A equals sine of angle C over C. I'm going to write that over there just to show you that this is going to be a very consistent way of doing this problem. So now I'm going to plug in values for each of these. So this will be the sine of 32 degrees over 8 equals the sine of 75 degrees over B. Make sure that when you put B, it doesn't look like a 6 and it confuses you. Very important. And then I would use the idea of finding the answer to a proportion with the cross product. So this would be B times the sine of 32 degrees equals 8 times the sine of 75 degrees. So what that means is B is going to be equal to 8 sine of 75 degrees divided by the sine of 32 degrees. And the nice thing about that is I don't have to find this value yet, because what I would have to do is I would round that one off if I was writing it out before dividing by sine of 32. So writing this all out together is actually very useful for us. And I'm going to enter that into my calculator, making sure it's in degree mode. It is. And what I end up with is B is approximately, when I round this to 2 decimal places, 14.58. Now I'm going to look at side C. Now before some of you say, hey, why don't we just use the Pythagorean theorem? Remember, this is not a right triangle. So I can't say a squared plus b squared equals c squared because it's not. Because it's not a right triangle. So we're once again going to use the law of sines to find that missing side. So when we bounce over here, this is again going to be the sine of 32 degrees over 8 is equal to, and this time it's going to be the sine of 73 degrees over c. And this looks like it's going to be very similar because of how close these are. So this is going to be c sine of 32 degrees equals 8 sine of 73 degrees. So c is equal to 8 sine of 73 degrees divided by the sine of 32 degrees. And this, again, will be an approximation. So I grab my calculator again, quickly enter these values in, and I come up with an answer of 14.44 as my value for C. I'll bring this back here. And the last thing we want to do, now that we have solved this triangle, is we want to take a look at what our values are. Does our answer make sense? Let's do that common sense check. So, smallest side is 8, smallest angle is 32, check. Largest side, 14.58, largest angle, 75, check. They are across from each other. And the last thing is 8 plus 14.44 larger than 14.58? Yes, it is. And our common sense check says that we probably have done this correctly. And this is how we would solve a triangle with angle, angle, side, given the two angles and the non-included side. All right, our second and final example for this lesson is what happens when we are given two angles and the included side between them. This is a little bit different, but as you're going to see using the law of sines, this will be very similar to how we solved our last example. So again, angle, angle, included side, or as we have it labeled here, I have a problem where angle A is 57, angle B is 14, and side C is 19. So you'll notice it's all of these values over here. There's a slight problem compared to what we did last time. When we looked at the law of sines last time with angle, angle, side, you were given both angle A and side A. It completed an entire one of those ratios in the law of sines. That's not given to us here. In fact, we don't have a ratio that's given to us right now where we have both the side and the angle. And in order to set up a law of sines, you must have both of those. So how can we get that? And the answer is just like we did the last time. The first thing we will find is the easiest thing to do. And here it's going to be, what is the missing angle that we have? So the missing angle that we have is angle C. We are given two angles, and we know with the triangle angle sum theorem that we are going to end up having a total of 109 degrees for angle C. Now this is an obtuse triangle. The last one we did was acute, and it doesn't matter if it's acute, obtuse, and even if one would end up being a right triangle, we would still have the same exact way of solving it with the law of sines. But the nice thing is, with the triangle angle sum theorem, now we have a ratio. So our key ratio now will be C and angle C, because that's what we were given, both of those values which are exact. So we can set up now our law of sines. The sine of C over C is equal to, and we're trying to find A, we're trying to find B. So just like last time, I'll set it up for A, and I'll set it up for B. So this will work for both of these situations. So the sine of C over C is going to be the sine of 109 degrees over 19 is equal to the sine of 57 degrees over A. Using the proportion and the cross product, this is A sine of 109 degrees equals 19 sine of 57 degrees. And then side A is equal to 19 sine of 57 degrees divided by the sine of 109 degrees. So A is approximately, based on that, and this is where we would bring our calculator back out, making sure it's in degree mode, and divide this out and get an answer of 16.85. And now it's time to find side B. Again, we will put in exactly the same values for C, 109 degrees over 19. This is now going to be the sine of 14 degrees, and that will be over B. So this is now B sine of 109 degrees equals 19 sine of 14 degrees. B is equal to 19 sine of 14 degrees divided by the sine of 109 degrees. And the last thing we would do, and again, this will be approximate because we will have to divide that. This is 19 sine of 14 divided by the sine of 109 degrees, which is approximately 4.86. So we put that back in here. The only thing left to do now is check the calculation. And to check it, our smallest side is 4.86. 14 is definitely our smallest angle. That checks. Our largest side is 19. Our largest angle is 109. That checks. And then 4.86 plus 16.85 is larger than 19, so this is a possible triangle, so that checks as well. So the answer we have is most likely correct. The last thing I want to leave you with is just looking how similar these two things are. If you look at the comparison between this and this, the numbers are virtually the same. So it's sine of 109 degrees over 19, sine of 119 and 9 over 19. Over here, this is the sine of an angle, and then the missing side. So when we're doing this and solving this, it will be very similar, and we'll be doing the same thing over and over again. This will allow us some consistency in trying to solve our values. So the first two cases of the law of sines are the easiest two. They are angle, angle, side, angle, side, angle. Find that third angle first, and then find your two sides using the law of sines.